Hello, well here's today's interesting project. What we have here is a modified kilowatt, some rather hazardous resistors, and a little analog digital converter board I built for another project. And what we have altogether is a computer interfacing kilowatt, that has much greater precision than, the actual kilowatt itself. So what you can see is, basically this is a modified kilowatt. I've brought out the current and voltage signals, which are these two wires. This is the voltage reference on this ADC here is actually 2.5 volts, so this is just a 10K and 10K divider on a breadboard just to bring the voltage down into the range that the ADC can work. And then this is I designed this for a project that at work that involves reading out just an inordinately large number of thermistors. Where's the right knob? Sorry. It's designed to handle reading the data out of as many as, it's 8 16 by 16 thermistor arrays at about a hertz. So what you've got here is, this is a parallax propeller microprocessor, and then these are digital isolators from Analog Devices. And then there's just a floating power supply. So this has the advantage of the fact that the USB interface and the microprocessor are completely electrically isolated from the analog to digital converter and the line voltage, because this is neutral right here. So I wouldn't be willing to plug this into my desktop computer if I didn't have the ability to have this completely isolated with a couple isolators good for a couple kilovolts. So obviously so what I did, this is kind of a rather dangerous way of doing this. I was very careful to check that this, the voltage on the ground, quote unquote, coming out of the kilowatt is indeed neutral rather than hot. Because if the wiring in the house is backwards, you could very easily have 120 volts. I'm in America, so it's 120 volts on the neutral lead, which would then make this whole thing hot and shock the shit out of you if you touch anything. So before I did anything, I was very careful to double check and reference against ground and so forth. So this is actually kind of the second version. So this was my initial version, which was it's an Arduino with an XP on it, but it kind of fell prey to the fact that the ADCs on the Arduino are slow and low resolution. This is 16 bits, and I think I'm sampling at about 40 kilohertz. Another thing is, Variac, is a nice resource just because that way I can vary the line voltage for calibration. And the switch on this actually breaks both the hot and the neutral, which is a good precaution. So what we have here is a rather not the most safe manner of measuring this. So what I've done here is I've broken the ground connection on this scope. So the entire body of the scope and all of the inputs are floating on the secondary of its main 60 Hz power transformer. So the advantage of that is that because, again, the ground on the scope is referenced to my line neutral, and I've measured the neutral to ground differential in this house, and it's about 2.5 volts. So this scope is currently, the whole casing of the scope is currently floating at about 2 volts. It's a good way if you don't have a proper isolation transformer to get yourself a floating, basically a floating measurement tool. The downside is that if you do something wrong, the entire casing of your oscilloscope will be sitting at whatever your mains voltage is. So you have to be very careful when doing so. In this situation we have voltage and current. I've confirmed that the voltage, so this is theoretically a 60 Hz sine wave, but you can see that it's inordinately flat topped. And I haven't really determined what's causing that, but presumably way too many switching power supplies with shitty power factor correction. So this here is the current waveform, and you can see that it really looks rather ghastly. This is a very, very shitty fluorescent that came with a $20 tensor lamp. But what I can do is I can swap the fluorescent for an incandescent halogen bulb. So now you can see that now that we have a proper resistive load, it's, the sine wave for the current matches the sine, or sine-ish wave for the current matches the sine wave for the voltage. and I can turn it up to get rid of the flicker, but unfortunately it's a little low frequency. One of the things that's interesting is I tried doing this exact same measurement with my OWON digital oscilloscope, and even with the, there was so much common mode noise coming out of the switching power supply that it basically swamped my signal in noise, because you get common mode noise and you get an AC ground loop, and it turns into a big issue. So it's one of the areas where having a nice, 60 hertz transformer power supply based oscilloscope is very useful. Aside from the fact that I like the controls on, an analog oscilloscope much better than the controls on a digital oscilloscope, because they're much kind of more immediate. This is my, let's see, my very nice 7904, and I've got a whole pile of plugins for it. There's some very nice things like this this has a very, very, very precise power supply, and you can subtract a fixed offset. So basically you get DC offset subtraction, so you can get basically you can look at really low frequency signals with an offset by subtracting the offset, and then you get down to 1 millivolt per div. And then it actually has a times 10 setting as well, so you can go to 100 microvolts. There's a lot of really great plugins for these series of scopes. They're probably some of the best analog scopes ever made. So here we have the other end of the system. This is the PC client at the moment. It's hacked together with Python and Matplotlib, and you can see it updates about once a second. And obviously I've put the fluorescent bulb back because you see the horrible spiky waveform, and here's the AC waveform. One thing of note is that because this is thrown together and I have a lot of flying wires, and the current voltage is, the current signal is rather small, there's a whole lot of noise. Presumably a lot of that's coming from the fact that there's a little brick switching DC to DC on the board, which is those things are terrible with regard to noise production. But now that I know that this works, I have plans to, I'm going to build a version using what are they, the Hall effect current sensors that I think Allegro Semiconductor produces, and presumably a little tiny 60 hertz onboard power transformer, because I'm only going to need about 20 or 30 milliamps. I'm going to basically design I'm going to make a very, very overly complicated outlet strip where I have current sensors on each plug, and maybe relays. I've been thinking about adding switchable capabilities to it. But, basically then I'm going to stick that in my little server closet and be able to track power usage in real time. You can probably see the auto scaling is a little schizophrenic. Yeah, anyways, it seems to work pretty well. It's not bad for something I put together in a couple evenings out of spare parts. You can see a lot of, basically array churn. Here's the, it's all command line, and then here's the source for it. And then the propeller, based off some older work I've done, and then you've got horrible messy stuff on the propeller, which is done in assembly, so I'm looking into XMOS devices because they seem really interesting, and I'm probably going to change microprocessors for the next device, just because I like the propeller model of multiple threads, because you can then do one thing in each thread, and it tends to lead to very easy to deal with code. But the downside is that there's no real compiled language for the propeller. You have an interpreted and you have assembly, and assembly is not fun. Anyways, that's what I've been working on. I figure somebody would think it's an interesting project. Hello there. So right here what I'm just doing is I wanted to confirm that the line voltage in my house was indeed as horrible as it looks. So what we have here is what's colloquially known as a really horrible idea. So literally what's going on here is hot. Shove some nails in the socket. Here we have three 100k resistors and a 4.7k resistor in series. Basically, so this is literally 120 volts right here, AC. I'm dividing it down, and then I'm just using the neutral back to the kilowatt because I didn't have another short clip lead. So I'm just looking at that with the DSO Nano, and this is really kind of a horrible oscilloscope, and the only reason I'm using it is because it's completely floating. It's battery powered, no ground reference. I'm pushing the buttons with the screwdriver, holding it with the back of the insulated handle, and then I plug the thing in and unplug it when I unplug it when I want to make any changes. So you can actually see that it's running right now, and you can indeed see that the line voltage in my house has got these horrible flat tops. And this has got me curious. I'm going to start looking around in other rooms and see if it's that bad everywhere, which means that the line voltage in my neighborhood is terrible, which is kind of intriguing, or if it's only that bad on the one leg of the breaker that I'm on, which means there's some weird switching supplies, because actually my computer's off right now, so I'm not sure what would be flat topping that. Anyways, I think it's interesting, and I thought it was just kind of amusing. So this is kind of a very much holy shit, don't touch it affair. But hey, that's how you go about hooking up, you know, electronics straight up to the line with no isolation. You know, this Variac, the switch actually breaks hot and neutral, so just turning this off is probably safe enough. But I like to unplug it as well, just as an additional safety measure.